Welcome to Understand the Math. In this video, I'll explain how to graph a basic sine and cosine function, and then how to graph a more complicated sinusoidal function. I'll define what the amplitude, period, phase shift, and midline are, go over steps for graphing a more complicated sinusoidal function, and then walk through an example problem. Before you begin, be sure to check out the video description below for a link to free guided notes that you can download and fill in as you watch this video. We'll begin by looking at how we can use the unit circle to graph the sine and cosine functions. The unit circle pictured here contains angles measured in radians and their corresponding coordinate points. To relate these angles and coordinate points to the graphs of sine and cosine, we'll draw a right triangle in the first quadrant. We'll label the angle as theta and the hypotenuse as 1, since our circle is a unit circle with a radius of 1. Our bottom length is x, and our right side length is equal to y. Since x is equal to cosine theta and y is equal to sine theta, we'll label our coordinate point as cosine theta, sine theta. To create the graphs of sine and cosine, we'll fill in this table for key values of theta. We'll begin with sine theta. Sine theta of 0 is equal to 0. Sine of pi over 6 is 1/2. And then we have root 2 over 2, and then root 3 over 2, and then 1. Sine of pi is equal to 0. Sine of 3 pi over 2 is -1, and sine of 2 pi is equal to 0. Let's now fill in the values for cosine theta. Cosine of 0 is 1. Cosine of pi over 6 is root 3 over 2. And then we have root 2 over 2, 1/2, down to 0. Cosine of pi is -1. Cosine of 3 pi over 2 is 0. And then lastly, cosine of 2 pi is equal to 1. Let's now graph sine theta. As theta goes from 0 to pi over 2, sine theta goes from 0 up to 1. Let's put those points on our graph of sine theta. We'll now translate the 3 points in between these points over to our sine graph. If we connect these points, we can see what the beginning part of our sine graph looks like. If we continue this process for all values of sine theta around the unit circle, we get a graph that looks like this. To graph cosine theta, we repeat the same process. Notice at the top that our cosine function starts at 1 and goes to 0 as theta goes from 0 to pi over 2. Let's put those points on our graph. When theta is 0, it's equal to 1. When theta is pi over 2, it's equal to 0. And then the other points look like this. We can now connect those points to draw our cosine function. Both graphs are periodic, and their shapes repeat every 2 pi units. The domain of our graph is all real numbers theta, Our graph extends infinitely to the left and to the right. We just wrote part of it going from 0 to 2 pi. Our range, or we can think of this as the amplitude, is all values from -1 up to and including 1. We'll now turn our attention to graphing a more generalized form of the sine and cosine functions. The sine and cosine functions are called sinusoidal functions. Sinusoidal functions are periodic functions that oscillate or repeat in a wave-like pattern. The general form for a sinusoidal function can be written like this. F of x is equal to a times sine b x minus c plus d, or f of x is equal to a times cosine b x minus c plus d. The absolute value of a is our amplitude. B is a quantity related to the period. C is our phase shift. And lastly, D is our vertical shift. Before we can graph these functions, we need to learn a little bit more about these 4 parameters, A, B, C, and D. The amplitude of our sinusoidal function is equal to the absolute value of A. The absolute value of A is the maximum displacement of the sinusoidal function from its midline. It measures the magnitude of the oscillation. In our graph, the x-axis is our midline. And we'll talk a little bit about the midline in a few minutes. We're going to begin by indicating the maximum displacement or amplitude in red. Our sine function in blue has an amplitude of 1. We can think of a 1 multiplying sine x. And our sine function in green has an amplitude of 2. We'll denote the period of our sinusoidal function as p. P is the length of one complete oscillation of our function before it repeats. In our graph of sine x, our period is 2 pi because that's how long it takes before the function repeats. We can write this mathematically in the following way. We say that f of x is equal to f of x plus p, where p is our period. That gives us f of 0 is equal to 0 plus 2 pi is equal to f of 2 pi. Our period is 2 pi because that's how long it takes for one complete oscillation of the function before it repeats. B is related to the period. P is equal to 2 pi divided by the absolute value of B. The absolute value of B and the period are inversely proportional. This means as one increases, the other decreases. To understand B better, let's look at 3 different sine graphs. Our graph in green is f of x is equal to sine of x over 2. Our graph in orange is sine of 2x, and our graph in blue is sine of x. If the absolute value of b is greater than 1, as in our orange graph, our period equal to 2 pi over the absolute value of b is going to be less than 2 pi. And this causes our function to compress horizontally. If the absolute value of b is less than 1, p equal to 2 pi over absolute value of b is going to be greater than 2 pi. And this causes our function to stretch horizontally, like you can see in the green graph above. The phase shift of our sinusoidal function is equal to c. C is the horizontal displacement of the sinusoidal function. If c is positive, greater than 0, the graph of the function shifts to the right. And if c is less than 0, or c is negative, the graph of the function shifts to the left. Our green sinusoidal function pictured here is the same as our blue sinusoidal function, but shifted to the right by pi over 2 units. We can write this as f of x is equal to sine x minus pi over 2. You can see that c is equal to pi over 2 and is positive, so the graph is shifting to the right. We can also write f of x as sine of x plus 3 pi over 2, where in this case our c is minus 3 pi over 2, and our graph shifts to the left by 3 pi over 2 units. The midline of a sinusoidal function is the line that the function oscillates around. The equation for the midline for our sinusoidal function is y is equal to d. If d is greater than 0, the graph shifts above the x-axis. And if d is less than 0, the graph shifts below the x-axis. These shifts can be thought of as vertical shifts. In our blue function, d is equal to 0, and our midline is y is equal to 0. We'll graph that in red. In our green function, d is equal to 2, and our midline is y is equal to 2, which we'll also graph in red. From the graph, you can see that the function oscillates around this midline. We'll now put all of this information together and graph an example sinusoidal function. I'll outline 6 steps that you can follow to graph a sinusoidal function. After you complete watching this video, I would encourage you to go to Desmos.com to graph this sinusoidal function. Desmos is great because you can get in and change the values of A, B, C, and D and see how the graph changes. I also have a blog post on my website that explains more about Desmos if you want to read more about it. The example that we're going to graph is f of x is equal to 2 sine of 3x minus pi plus 1. We're going to find the amplitude, period, phase shift, and midline of f of x, and then graph the function. Our first step is to rewrite f of x in general form. Let's write down what that general form is. F of x is equal to a times sine times b quantity x minus c plus d. If we write our f of x in this form, we get 2 times sine. Now we're going to pull out the b, which is equal to 3. X minus, and then instead of pi, because we pulled out a 3, we have to write a pi over 3, plus our midline, which is 1. So now our function is in our general form, and we can easily see what a, b, c, and d are. Our a is equal to 2. Our b is equal to 3. Our c is equal to pi over 3. And lastly, our d is equal to 1. For step 3, we're going to find the amplitude, period, phase shift, and midline. The amplitude is the absolute value of a, which is 2. The period is 2 pi divided by the absolute value of b. So this is 2 pi over 3. The phase shift is equal to c, which is pi over 3. And the midline is y is equal to d. So that gives us y is equal to 1. Let's go ahead and let's highlight these values. In our fourth step, we'll find the x values for one period of our function. We're going to start with the interval from 0 to 2 pi, and then we'll adjust x. 0 to 2 pi is our interval for sine x. And that's always the starting point. I've included the amplitude for sine x because we're going to need that in our fifth step. We'll now adjust for our period and our phase shift. We're going to begin by dividing each of our x values by b. Our b is equal to 3, so we'll divide each of our x values by 3. So this gives us 0, pi over 6, pi over 3, pi over 2, and then lastly, 2 pi over 3. From this, we can indeed see that our period is 2 pi over 3, what we calculated above. We're now going to add c, or pi over 3, to each of our x values. This gives that x starts at pi over 3, and then pi over 6 plus pi over 3 gives us pi over 2. Pi over 3 plus pi over 3 gives us 2 pi over 3. Pi over 2 plus pi over 3 gives us 5 pi over 6. And then 2 pi over 3 plus pi over 3 gives us pi. I know a lot of students struggle with those fractions, so if you're struggling with that, just hang with it, and you can maybe add the fractions on the margins and see how we got these answers. Let's now make a note that our phase shift is pi over 3, and we can tell that by looking at the change in our first x value. If you're finding this video helpful, give it a thumbs up and also consider subscribing to my channel. In the fifth step, we're going to find values for y or f of x. Let's begin by writing down the interval that we found from step 4. Our function starts at pi over 3, and it goes up to pi. And we'll fill in the points in between. This is what we had on the previous page at the bottom. We'll now take our value for sine that's written in blue and multiply it by a. So let's make a note that a is equal to 2. So our blue values are going to get multiplied by 2. So this is 0, 1 times 2 is 2, and then 0. Minus 1 times 2 is a negative 2, and then a 0. To account for the vertical shift, we're going to add d. So we're going to add d is equal to 1. So we'll take our values in blue and we're going to add 1 to them. So this gives us 1, 2 plus 1 is 3, 1, minus 2 plus 1 is minus 1, and then 0 plus 1 is 1. Our last step is to construct the graph of our function. We'll begin by writing down the x values in our interval. We're going to start at pi over 3, we'll end at pi, and we'll plug in the values in between. Pi over 2, 2 pi over 3, and then 5 pi over 6. We'll then draw our midline, which is y is equal to 1, or in this case, f of x is equal to 1. Next, we'll put in our adjusted sine values listed above. We'll start at 1, and then we go to 3, back down to 1, we go down to -1, and then we end at 1. The last step is to connect our points and draw our graph. And then I'm just going to extend the graph a little bit so that we can see that it's going to continue to the left and to the right. I would suggest that you study the steps we've gone over and then complete this example on your own.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.